Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck. As we continue our journey through mathematics, we are journeying through conic sections as well. Today, we're going to be talking about the last of our conic sections, hyperbolas. So if you remember conic sections, that's what happens when you take the double napped cone, and that double napped cone, when you cut cross sections of it, aka conic sections. The first conic section that we can get if we take a horizontal cross section is our circle. And then if we angle that cross section a little bit, that's where we get our ellipse, followed by, if we have parallel to those lines that form the conic section, if you remember from our video, you get our parabola. I know you can't see the parabola here, but you get our parabola, followed by the hyperbola. And today we're going to be discussing our hyperbola. So what is a hyperbola? So if you look at the definition of hyperbola, it's a collection of all points whose differences of distances from the two foci are constant. Well, if you remember, let's take a look back at the ellipse. Our definition of an ellipse is what happens when you take the sum of these two distances, meaning this distance here and this distance here. These are always going to be 10 no matter what. And those distances end up being the value 2a. I skipped over a little bit of the algebra behind it, but that distance is always 2a. If you notice our major length, which is sometimes called the major axis or the major radius. That length of 5 gives us a total length of the major axis of 10. And so that length of 10 is what's going to happen if we take this point all the way around. If I change that length, then if you notice, the major length and the distance sum are always going to be double. Now, that was the ellipse. We discussed that last time, but what happens if we make C bigger than A? Then what happens is any point that's going to be along this hyperbola now, if you notice, the sum is going to be changing, but the difference is not. So that's what we mean by the difference of distances. So this distance minus this distance will always be constant. And that constant value is still going to be 2a. Even if I move the point over here, just due to the algebra behind this, this is always taking f2 minus f1, which is why this says that difference is negative. It really is a positive value. But I did want to show you that even if the point's over here, it's going to be the same difference no matter what. So when it comes to our hyperbolas, a couple different things. If you remember with the ellipse, due to the nature of this program, this always shows a horizontal orientation, but we can have a vertical orientation if A was underneath the Y value. Now, as you take a look at the hyperbola, our hyperbolas, we can have a variety of hyperbolas. A hyperbola can be very, very narrow, which means A is significantly bigger than B. Or we can have a very, very wide hyperbola, which in this case, our A value is actually going to be much, much smaller than B. So with an ellipse, A was always bigger than B, but this is going to be a big difference when it comes to the hyperbola. The A can be smaller than B. So let's take a look at the notes a little bit more carefully, and we can go through this. So our transverse axis is what we used to call the major axis. Now, the reason why we call it a transverse axis has to do with we now have a different shape, different things are happening. So that transverse axis is what we, again, considered the major axis before. The vertices are pretty much the same. The vertices are going to be really our shortest distance. This value is 2a, which means that our vertex is always going to be a units away. So the center, still the same, one more time. It's the midpoint between the vertices, but also what that does form is it's not what we call the minor axis. Again, we change from major and minor axis to transverse axis and then conjugate axis. So the conjugate axis is what we used to consider the minor axis. One of the reasons why we don't call it a minor is because, I mean, first of all, it's a different shape, but second of all, remember that minor axis or that conjugate axis could end up giving us a much, much larger value, so it's not really minor in that sense. Now the branches are what we call the hyperbola as it extends on to infinity this way and this way. Those branches, what we like to do with those branches is we like to form two lines, and those lines are the asymptotes. If you remember, asymptotes are what we use to create that distance as we go on to infinity. Those asymptotes are going to be the basis of how we are going to be forming our hyperbolas. So taking a look at this graph of the hyperbola, what we are going to do is we are going to, our goal here, we are going to say, what is our A value? And we're going to make our vertices from that. We are going to say, what is our B value? And we're going to make what I consider the box. Now, you don't have to make the box. The box is just something that is very helpful to help us draw the asymptotes, because the asymptotes, or the which lead to the branches of the hyperbola, are the defining features of the hyperbola. So if you notice, going back to GeoGebra, if you notice, even if we have a circle, you can make a box around that circle. With the ellipse, we never really made a box, but you can still make a box around that ellipse to contain the ellipse. Now, this time, the hyperbola is outside of the box, so the box helps us define it, but it doesn't actually contain it like it used to. And there's so many different things that you could do with conic sections. Very, very amazing. Like anything in mathematics, the more you journey into it, the more you're going to see so many different aspects of the math, which is why I love the math. So without further ado, let's take a look at some of the comparisons between ellipses and hyperbolas. When it comes to an ellipse, so with an ellipse, we know that A has to be bigger than B. Now, when it comes to the hyperbola, A can be smaller than B. And I showed you an example of that. I showed you an example of that before. Now, one of the reasons why we defined A to be bigger than B for the ellipse is because, if you remember, C squared equals A squared minus B squared. So when it comes to C squared equals A squared minus B squared, A has to be bigger in order for us to have a C value, and also to be imaginary. Now, when it comes to hyperbola, C squared will equal A squared plus B squared. So this distance A here, this distance B here. So this distance C, let me change colors so we can see that a little bit better. But this distance C is actually equivalent to this distance. I know that's hard to tell, and ironically, it's actually very, very hard to prove. The last time I looked at it, I saw there was more than a 2-page proof to show why that's true, which seems kind of contradictory to me because it almost looks like a Pythagorean theorem, but it's not. So what else when it comes to an ellipse? So the ellipse is contained, so it's contained within the box. So within the box, where the hyperbola is outside the box. So big joke about, hey, let's think outside the box. But how we're going to construct the hyperbola is going to be very, very similar to how we constructed the ellipse. Now, when it comes to the equations, this idea of the difference between the two distances actually will show up in our equation. So looking at the equation, these equations look very, very similar to the ellipse, which is going to be the last thing we're going to talk about. So where we had x squared over a squared plus y squared over b squared equals 1, this actually shows the sum of the two distances is 1, where now it's going to be x squared over a squared minus y squared over b squared equals 1. So again, that key difference of the sum for the ellipse and the difference for the hyperbola are going to show. But again, everything else is going to be actually very, very similar. So let's put it all together. So find the equation of hyperbolas with the given information. So let me go ahead, like I did before when it came to the ellipses, let's draw this out. That the foci, I can have to scoot this over just a little bit more so I can put this on here. So the foci are going to be here and here. So there's my two foci. So when it comes to the foci, we know that this distance of 12 actually represents our C value. So C is 12. Now our vertex, and I'm going to do vertex in a different color, but technology. So our vertex is only 9 units away. So this is how we know that this, again, is going to be a hyperbola rather than an ellipse, because the vertex is a smaller distance away. So what's happening is, if I were to sketch it out, our hyperbola should look like that. So that vertex gives us our A value. So our A is 9, our C is 12. What's naturally left for us to find is, what is B? So what is B? To find B, we know that C squared will now equal A squared plus B squared. So C squared, which is 12 squared, or 144. So 144 will equal A squared, which is 81, plus B squared. So B squared ends up equaling 144 minus 81 should give me 63. Now that means B is the square root of 63. So when it comes to our equations, one of the things that we do need to look out for is the orientation. The orientation, if we have what we consider more of like a horizontal, or the transverse axis is parallel to the x-axis, which is what we see here, then it's x squared minus y squared. But if we go up and down, this one actually will give us the y squared minus x squared. So y squared over a squared minus x squared over b squared is 1, where this one is x squared over a squared minus y squared over b squared is 1. Now when it comes to hyperbola, remember a does not have to be bigger than b. A can be smaller now. But I consider this term right here to be kind of the dominant term. That dominant term is because my transverse axis is horizontal, where this one, my dominant term, is because my transverse axis is vertical. So let's put it all together to finish off this problem. We now have b squared. We know that this is horizontal. Since it's horizontal, it's x squared over a squared. Let me write that down. Because it's horizontal, it's x squared over a squared minus y squared over b squared equals 1. So we know a squared is going to be 81. We know b squared is going to be 63, which is what we found. And so there is our answer. For problem number 2, drawing it out, what we should have is our foci, our 0 plus or minus 14. Now I sort of skipped over that before, but this actually tells us our center is 0, 0. Kind of naturally assume that, I apologize. So our C ends up being 14. And this vertex tells me A is going to be 9 again. 0, 9, we were only given one vertex, but due to the symmetry, we should also have a vertex down here. Now, if I were to sketch the hyperbola, it's going to look something of this nature. It's important for us to actually have those asymptotes in there, and we're going to analyze those a little bit later. But when it comes to our hyperbola, we know that our hyperbola is vertical. Because it's vertical with the center at 0, 0, I know it's going to be y squared over a squared minus x squared over b squared equals 1. And we're just left to fill in the information that we know and that we find what we don't know. So y squared over a squared ends up being 81 equals, now how do we find b squared? Once again, we're going to go back through our relationship that c squared is a squared plus b squared. So c squared, 14 squared is 196, a squared is 81. So b squared ends up equaling 115. So that would be x squared over 115 equals 1. So there's our equation. And if you notice, when it came to problem number 1, we had, let me change colors here quickly. We did have A was bigger than B because 81 is bigger than 63. So 9 is bigger than the square root of 63. Where in this case, we have A is less than B. And I'm highlighting that because one of the biggest mistakes people make is to say, oh, it has to be the bigger number. No, that's only true for an ellipse. Let's go ahead to graph it. Now, based off of our equation, our center should be at 0, 0. The reason why our center is 0, 0 is because nothing is being subtracted. If you remember x minus h squared, we did this with the ellipse. So over a squared plus et cetera, et cetera. There are h and k are both 0, 0. Let's go ahead and plot that. And I think I have a few residual things on my graph. Okay, so what is a? Because it's x squared minus y squared, our a should be 4, because the square root of 16 is 4. Our b is going to be the square root of 36. Let me go ahead and write that, which is 6. So that tells me our b value is 6. I'm going to go out, and then our c value. How do we come up with our c value? C squared equals a squared plus b squared one more time. So that would be 16 plus 36, which is 52. So c is the square root of 52, which is just over 7. So more than 7, because 7 squared is 49. So c is the square root of 52. Now, the question is, which way is which? Because this is x squared minus y squared, we know that this is a horizontal orientation. So we're going to go out 4 units horizontally because that's what A is. One of the things I like is, if you notice, whatever is underneath the x is what we're going to do x-wise. Whatever is underneath the y, we're going to do y-wise. Now, when it comes to the hyperbola, the orientation is just based off of which one comes first. So what's underneath the x is 16. So we're going to go horizontally 4 units each way. What's underneath the y is 36. We're going to go vertically 6 units each way. And this is how we create that box. And again, the whole point of the box is really more of to define the asymptotes. So I'm actually going to plug those asymptotes, or put those asymptotes in right away, because that's the biggest benefit of the box. The asymptotes really are the diagonals of this box. And those diagonals will form the branches of the hyperbola. So from that equation, horizontally and vertically, we can always make that box. Now let's define which ones are the vertices, which is where that horizontal orientation, the x squared minus the y squared, tells us that that horizontal 4 is going to be our vertex. So let's label that V for vertex. And then our foci, these are sometimes called covertices. Our book tends to not give them a name, so I'm not going to. So our vertices are 4 units away from the center, so plus or minus 4 is 0. Our foci are going to be just over 7 units, which would be right about here. So there's one focus, there's the other focus, and then the hyperbola will go vertex to branch, or vertex to branch, vertex to branch. Ooh, that one's a little squiggly. Vertex to branch. And our foci are plus or minus square root of 52, comma 0. That's not the best mathematics. We know that that should be 2 times the square root of 13, comma 0. Now our asymptotes. I prefer to, we can do 2 separate asymptotes. In order for us to find the asymptotes, I tend to look at this as what is my rise and what is my run. So in this case, our rise is our vertical distance, which would be 6. So the slope of each asymptote, the slope is our rise over our run. Our rise we said was 6. Our run we had as 4, which gives us a slope of 3/2. Now I like the point slope form of a line. So y minus 0 is 3/2 times x minus 0, or more simply, y equals 3/2 x. Now that is only for that first asymptote drawn right there. Now what about the other asymptote? Well, because of the symmetry, that other asymptote is really just a negative slope as opposed to a positive slope. So our asymptotes I will put as y equals plus or minus 3/2 x. So one of the reasons why I'd like the point slope is the moment we change the center, then our asymptotes will still be going through that center point. Okay, so on to problem number 4. With problem number 4, if you notice that we are no longer in standard form, so our first step is to get it into standard form by dividing by negative 144. And why is because when it comes to the equation of any conic section, we like to set it equal to 1. So when we divide by negative 144, that gives us x squared over 16. 144 divided by 16 is 9, so that's a negative 9. We have a negative 4 over 144. 4 and 144 simplify or reduce to 1 and 36, but now it's going to be y squared over 36 equals 1, which, if you notice, the negative is now first. I don't like that. Let's put it as y squared over 36 minus x squared over 9 equals 1, just so we can get it into our standard form. Our center is 0, 0 because there's no h and k here. Now underneath the y, vertically, we're going to go out 6 units because that would be the square root of 36. Horizontally, we are going to go out 3 units because that is the square root of 9. This is where I'm going to form the box. And if you remember, last time I said this is the time we're going to be drawing in our asymptotes. Let's go ahead and draw in our asymptotes. And I'm going to go one step further and say, let's create the equation of these asymptotes. What is our rise? Our rise is our vertical distance of 6. So our slope is our vertical distance of 6. Our run is our horizontal distance of 3. So that reduces to 2. And both centers, let me just go ahead and put it as y minus 0, is plus or minus 2 times x minus 0. Or more simply, y equals plus or minus 2x for us to be able to find the equations of our asymptotes. Now, which one is A, which one is B, which one is C? Going back through, A is underneath what I consider the dominant term, which would be the first one when we put it in standard. So A should be 6, B equals 3. And let's go ahead and actually draw on the hyperbola. Because it's y squared minus x squared, since it's y squared minus x squared, we know that this is a vertical format. So that vertical format should look like this. If you notice, this is a very narrow hyperbola as opposed to the previous one, which is a very, very wide hyperbola. And what constitutes the narrow versus the wide? It's all the relationship between the A, the B, and the C. And speaking of C, let's go ahead and find the C. C squared will equal A squared plus B squared one more time. So 36 plus 9 is 45. So C is the square root of 45, which simplifies to 3 square root of 5. Now the square root of 45 is just less than 7. So just less than 7 on my graph should be right here. And just less than 7 should be right here. Now, if you notice the relationship that, let me change color so we can see it a little bit clearly. There is not much difference or distance between the focus and the vertex here, which is why we have the narrow hyperbola, versus we have a much more extended distance here, which is why we have the wider hyperbola. So as the focus moves away from the vertex, that's what creates the bigger hyperbola. We could take a look at this as our focus length gets bigger and bigger. If you notice, this distance from the vertex is getting bigger and bigger. That's what creates the wider one. Now, if our focus is really, really close, if our C value is really, really close to the A, that's where we get the narrow hyperbola. So our vertices, just to finish off our problem, our vertices are going to be, since it's a vertical format, 0 plus or minus 6. And our foci are going to be 0 plus or minus 3 square root of 5. Now, if our center changes, then that center change will cause a change in those x values. Likewise, if our center changed, our center change would cause a difference in those y values. Now, going back to the equation, if you remember what I talked about when it came to the ellipses, I tend to not focus as much on this box, but it's a very, very helpful tool as you're beginning, as you're looking through it, just to see how these change. I don't encourage the memorization of all this information because all of this is more geometrical. So now we get on to problems 5 and 6. If you notice with problems 5 and 6, both of these are what we call the general form of the conic section. We're going to be exploring that a little bit more in our last lesson, SNF. I was very, very sad that next time is going to be our last lesson. But we're going to have to get this into our standard form, which is where we have the x squared minus y squared equals 1, or y squared minus x squared equals 1. So without further ado, I am going to have to work with my technology here. So 9x squared plus 36x minus 4y squared plus 16y equals 16. What I am doing is completing the square. So complete the square. To complete the square, the first thing we need to do is factor out the leading coefficient. Now, warning, please make sure you factor out the -4. When you factor out the -4, it is going to change the sign of this to a negative. And why that's very, very important is because now that's going to change where our center is when we finish our work. So please, please, please be very, very careful of that one. Now let's actually complete the square. Half of 4 squared is 4. Half of negative 4 squared is also 4. But how do we work on the other side? When it comes to, let me make this 4. This 4 did get multiplied by the 9, so I like to show it as we are going to be adding 9 times 4 over here. And when it came to this 4 right here, that 4 got multiplied by negative 4, so this is negative 4 times 4. So 9 times x plus 2 squared minus 4 times y minus 2 squared will equal 16 plus 9 times 4. 9 times 4 is 36, minus 4 times 4, which is 16. So 16 plus 36 minus 16 is just 36. And now when I divide by 36, I will get my standard form, which is x plus 2 squared over 4 minus y minus 2 squared over 9 equals 1. So the very first thing I want to do is identify my center. My center is going to be h comma k. So my h is negative 2, and my k is a positive 2. If you remember, it's x minus h and y minus k. So our center is at 2 comma negative 2, which should be right here. So paying attention to these details is going to be very, very important. Horizontally, we are going to go at 2 units from my center. And that creates my vertex, since I know this is x squared and minus y squared. Let me go ahead and label those as v at the moment. So horizontally, I go out 4. Vertically, I'm going to be going out 3, because that would be the square root of 9. At this point, let's form the box. And the whole reason why I want to form the box is so I can fill in my asymptotes, which will look like this. All right, so let me label my vertices since I have those on there. My vertices are going to be 4 comma negative 2 and 0 negative 2. Please do not leave that as negative 2 plus or minus 2 comma 0, which ironically, my center is at negative 2 comma 2, which let's change that to be right there. That was a pretty big mistake that I made, and I'm glad I actually caught that with the negative 2 plus or minus 2. So let's go ahead and now redefine our vertices. Our vertices are going to be 0 comma 2 and negative 4 comma 2, followed by our asymptotes, which are asymptotes. This is where I like to use the point slope form of the line. And now I'm going to color this briefly just so you know what I'm referring to. I'm going to be using this equation to help me, because when it comes to this equation actually will tell me that y minus 2 has to be matched up with what I have there, because the point that we're going through is negative 2 comma 2. So our slopes times x plus 2. If you notice, that's very similar to what I have in the equation there. But what's left for us to find are the slopes. So our slopes are going to be rise over run. And this is where I like to just look at these values. And our rise would be the square root of 9 is 3. And our run is going to be the square root of 4, which is 2. So our slopes are plus or minus 3 halves. Now, what is A, what is B, what is C? In many ways, what's important about the A is really graphing this. Let me go ahead and sketch the hyperbola in here while I'm thinking about it. If you notice, there is no specific process to find or to plotting all of this. All this information is there. It's just us taking the information and putting it on the graph. Our A is going to be our dominant variable, and our dominant variable is going to be the horizontal one since it's x squared minus y squared. So our A is going to be the square root of 4, which is 2. Our B is the square root of 9, which is 3. And to get our C squared will equal A squared plus B squared. You've seen that enough, so that's 4 plus 9. C squared ends up being 13, so C is the square root of 13. Let's go ahead and make those our foci. Now when it comes to our foci, our x coordinate is 2, negative 2, excuse me. So negative 2 plus or minus our C value. So plus or minus our C value. And then our y coordinate is still that constant too. So negative 2 plus or minus the square root of 13, comma 2. The square root of 13 is just under 4 units away. So when I go to plot that, 1, 2, 3, 4, so just under 4 units, which would be right here. 2, 3, 4, so just under 4 units, which would be right here. So those are my foci. And I believe I have all of my information there for my hyperbola. And then I'll walk through this last one a little bit more quickly, just because a lot of the things are going to be the same. But let's pay attention to the detail, and I'm saying that for myself, just like I'm saying that for you guys. One small move and your entire hyperbola is wrong. And once again, I'm glad I caught that error. Don't like that I made that error, but you know what? Mistakes happen. And so it's us learning through our mistakes. Factoring out the 9 here, negative 9 here, will lead us with a positive 16. So 144 divided by 9 is 16. And then factoring out the positive 4 here, that would be y squared plus 8. It's 548. So half of 16 squared, so 8 squared is 64. So x squared plus 16x plus 64. I'm going to compensate right now by saying what's happening on this side, negative 9 times 64, because it's very, very easy to lose sight of that. Let's continue on. Plus 4, half of 8 squared is 16. So I am also adding 4 times 16. So negative 9 times x plus 8 squared plus 4 times y plus 4 squared will equal 548 minus 9 times 64. And I'm struggling to find my calculator. I didn't have it up today because I didn't think that I was going to need it. And obviously I was wrong. So I now have my calculator. So with the calculator, 9 times 64 is 576. So what I'm looking at is 548 minus 576, and then plus 4 times 16, which is 64. So 548 minus 576 plus 64 gives me 36. So that's 36. So when I divide everything by 36, I will have negative x plus 8 squared over 4 plus y plus 4 squared over 9 equals 1. And what that means is we're going to have to rewrite this if we wanted this in our standard form. And I'm running out of a lot of space. Let me put it at the bottom. This really should be y plus 4 squared over 9 minus x plus 8 squared over 4 equals 1. Let's plot our center, and let's be very careful about our center. Our h is going to go with our x. So x plus 8 squared, so that would be center of negative 8. And then our y plus k squared, our center should be, or our y value should be negative 4. So negative 8, negative 4 should be right here. There's my center. The question is this a horizontal or a vertical? Well, let's actually say horizontally, we're going to go out 2 units. Vertically, we're going to go out 3 units. And so let's create our box. And from that, we can create our asymptotes. And is this a vertical or a horizontal orientation? Because it is y squared minus x squared, so y squared minus x squared means it's going to be a vertical orientation, which should be right, or looking like this. And now filling in the information, the a goes underneath the dominant variable, which is y, so a is the square root of 9. B is going to be the square root of 4. And kind of like what we had before, that's 3 and 2, so C is the square root of 13. So technology, I love it. Square root of 13 is going to be slightly less than 4, so there's one focus. There's going to be the other focus. And so our vertices are going to be, since it's a vertical orientation, -8, -4, plus or minus the square root of 13. Oops, that was actually my foci. I'm going to go ahead and move those down to the foci. The vertices are going to be -8, and then it'd be -4 plus 3, which is -1, and -4 minus 3, which is -7. So if we have a square root, you're welcome to put it as plus or minus, but please don't leave the vertices that way. In our asymptotes, I'm going to follow my standard form. Y plus 4 equals something times x plus 8. Now our slope is going to be rise over run. Our rise is going to be the number underneath the y. So our rise is going to be plus or minus 3. And then our run is going to be 2. The square root of 4, which is 2. So last but not least, we have these 3 problems. And these 3 problems, we are going to find our pieces of information. A piece of information we have here are we're given our asymptotes, or y equals plus or minus 4x. So I'm going to sketch all that information out. So a slope of 4 is going to look like that. Slope of -4 would look like that. This actually will tell us our center. The fact that there is no shift, since there is no shift, we know that this is going to be x squared and y squared, not x minus h squared and y minus k squared. Our vertex is 0, 12. So that fact tells us it's going to be a vertical orientation. So automatically I know it's going to be y squared minus x squared equals 1. Again, there's no shift, so it's not y minus k squared. Our vertex gives us our a value. And since this is a vertical orientation, since it's going to open up like that, it's going to be y squared over 12 squared. So I know that's 144. What we're left to find is, what is that value underneath the x squared? So this should be our b squared value. So we know a is 12. We don't know b, but this is where our slopes are going to kick in. The fact that our slopes are 4, that tells us our rise over our run has a ratio of 4. And so I'm going to put that ratio of 4 over 1. Now, we know that that ratio of 4 over 1 is our ratio. In this case, it'll be A over B. And the reason why it's A over B is because this is a vertical orientation. Since it's a vertical orientation, that number underneath the Y is our A, the number underneath the X is our B. I look at it as rise over run. That rise over run gives us a 12 over that B value ratio. What is that B value? Now, if I look at this, this is saying 4 will equal 12. That's a 4 equals 12 over B. So 4B equals 12, which means B equals 3. Since B equals 3, then I can just finish off my equation. Y squared over 144 minus x squared over 9, or 3 squared, which is 9, equals 1. There's my equation. Problem number 8. Once again, our slopes are plus or minus 1. So our slopes are plus or minus 1. What's special about this? This is a special hyperbola, which I can't think of the name of it right now, unfortunately. But plus or minus x means my a and my b values are going to be the same. This is where I'm going to rely. So this tells me that a equals b. My focus is 6, 0. So what I'm going to emphasize here, the fact that my focus is 6, 0, means my c value is 6. This also tells me it's a horizontal orientation. And I'm left to find my A and my B value. But if I notice, A and B end up equaling the same thing. So what I can do is look at it. I'm going to put this as, since it's horizontal, x squared over a squared minus y squared over b squared equals 1. Now A and B are the same, so I'm going to generically call it the variable, let's say s. So s squared plus s squared, because that represents a squared plus b squared, will equal c squared. So c squared is 36. So solving this, I get 2s squared is 36, which means s squared is 18. So s, really I want to know my s squared because this tells me this is no longer a squared. This is no longer b squared. So x squared over 18 plus y squared over 18 equals 1. Kind of jumped through a little bit of logic there, but the goal was a and b were the same value. That's how we were able to figure out what our equation is. Now that we have our center shifted, let me go ahead and sketch it out. Very, very important for me to sketch it out. 4, -1 would be right here. I have a focus of 7, -1. So 7, -1, which is here. Immediately I can say this is now a horizontal orientation because the focus and the center are lined up on that transverse axis. Let me go ahead and sketch a transverse axis in here. So because it's horizontal, I know it's x minus y squared. So x squared minus y squared. I am going to immediately set up that because that's my horizontal orientation tells me. Now, since I'm given my center, I can go ahead and fill in my center. That's x minus 4 squared and y plus 1 squared. Now the question is, what is A, what is B, what is C? So that I could figure out all the information. My vertex, if I put that piece on here, 6, -1, now that tells me what's my distance between center and vertex. That distance is 2. So 2 squared is 4. And center to focus is going to be 3. So that means C is 3. So C squared will equal A squared plus B squared. So that means B squared is going to be 5. And our very, very last problem, I'm given a vertex of -2, 7. So -2, 7 looks like right here. There's my vertex. And then I'm given my asymptotes in point slope form. The benefit of having my asymptotes here is, technology one more time, benefit of having my asymptotes is this actually will give us the center of our graph. So our center should be at -2, 3. So -2, 3, which is right about here. And based off of the layout, I know this is going to be vertical. So that's where I'm going to have y minus 3 squared minus over x plus 2, or squared over equals 1. What we're left to do is figure out what is a squared and what is b squared. Well, what is that distance from center to vertex? So from -2, 3 to -2 center, that distance is 4. So 4 squared will give me 16. And I'm left to find my b squared. So if you remember, c squared equals a squared plus b squared. Well, how am I supposed to, actually, I'm not even going to be using that in this case. This is where I'm going to be using my slopes. So my slope ratio is 2/3. So my slope is 2/3. Because this is vertical, since this is vertical, this is going to be A over B. And the reason why it's A over B is because it's the rise over run, and our rise is right here. So our A is going to be 4, and we don't know our B value. So 2/3 will equal 4 over B, and hopefully you can see that B ends up being 6. So our last equation is y minus 3 squared over 16 minus x plus 2 squared over b squared, 36, is 1. And there we are. This is one long video, but that's it. So good luck, everybody, on all of your notes.